Calcutta University and studied in Presidency College. And then Masters from Science College, that is also Calcutta University. Did his PhD in IIS Bangalore, and then he was a postdoc at Amsterdam. And he is a faculty of SN Post Center from November 1999. Currently, he is a professor there. His research interests include many things. Among them, the statistics and dynamics of soft nanosystems, biomicromolecular complexes, and he loves to model large scale behavior of biomicromolecular complexes, and of course colloidal systems. So with this brief introduction, it's real pleasure to welcome you to this colloquium. Please start.
So thanks to Kolkata and British for inviting me to give this colloquium, and of course the owner will say almost everything about me and so much kind words. But it's exciting for me because I distinctly remember the first day of my BSc class psychology, and the very first day, a very young man came and he started writing on the wall. That's the first lecture that we had, and he started writing on many things from the book. And I was completely lost. I came from village through this people, and the completed lost. I didn't understand, could make any take out of it. And then after 40 minutes or so, he left. And then I asked my friends, will you follow it? Everyone is laughing at me. Then I was at least certain that not only me, other people are also laughing. So I'm not thinking that big. So then we get dropped out with the moment the class ended in 5 minutes. Other came, and one of them was shocked. So they said, how was the class? Come on, such a strange class. No one would make anything. It wasn't hardly a night, but it good health. I think. And then he just part of writing. And on LinkedIn, when he wrote us, you follow this. If you cannot follow this, you cannot have these honors. So let me start. Don't hesitate to stop me if you want to have some clarification or something. It's really big. Center we have the board and lots of big area. It's one internal and it's really board. And that's why people are saying, yeah, I can imagine. Okay. So I work in basic sciences at the Department of Physics of Complex Systems, and partly also Department in Biosciences. There's only a way of the names, because in the end what comes out is that I try to work with statistical mechanics of systems, which are complex in some sense. I try to define what complexity is meant. First, the kind of stock matter is worth for analysis, particularly in the scientific community, where people actually we can describe a hierarchy of something. What is something? It could be length scale, it could be time scale, etc. Now, what does I mean by hierarchy? I just try to explain in terms of example, which is like a typical example of so-called soft-matter systems. It's colloids. Colloids is something that I'm sure many of you already know about, right? You know things like Tyndall effect, etc. I'm sure that you also know that Robert Brown, for the first time, happened to see the zigzag motion of human brain, and that's in fact the prototypical motion of such systems. Now, why is soft-matter and why is not this? The reason for significant colloids are big molecules. How big? Micrometer. How much big or small? By comparing to the wavelength of visible light. Wavelength visible light of what can be visible with data just in something, and something that you see every day, smoke, for example. You can see the smoke, right? The color of smoke is more opaque just because they can scatter light range. And then many other examples, blood is a colloid, milk is a colloid. So colloid means some system which has got bulky component. For example, if you think of, let's say, or maybe even simpler example, take paint. Paint and latex particle. The latex particle submerged in some oil medium is paint. Now you see the medium is very important in this chemistry. This essentially means the system is a dispersion of one phase into another phase. But in this dispersion, important thing is that one phase of the dispersion, the medium, is much tinier compared to another phase. If you take, let's say, paint, as I said, iron molecules, the largest maybe about 10 angstrom or so. And I told you, the colloidal particles are, these are like paint particles, latex particles. They are micrometer. So you can see how big is the difference in size of the dispersion and the system, let's say, the colloidal system. And that's what we call it colloidal suspension. The suspension is a very important word in this text because that defines iron. Now, example as written here, actually the asking EMF particle, the horizon is a clay particle, but many of the ARTs in the device, they even, in fact, biological cells, they as an activation variable, they move indeed like a software, which we mentioned before. So the example of this kind actually is numerous, and it can be, as I said, that colloidal particles like big particles in the medium. The medium has the property is like a box. Now what the meaning of box? Box has got numerous divisors. I'm sure that many of you, all of you have read common elements, right? Common elements of the box. What is a box? Box is something where the number of billion becomes infinitely large. Hence, the perturbation is not going to disturb the box. And these are the particles necessary and talking about motion in the box. Now, what are the mechanics? First of all, the lens here, as I said, something like starting 100 nanometers to 10 nanometers. We know how to typically called nanoparticles. But nowadays, even nanoparticles of the order of 50 angstrom are also called colloidal because they are very similar in behavior and physics. Something larger than that, then macro, of the order of few, let's say 0.1 millimeters, then we found the regime of granular physics. So this is how actually the lens dictates the physical laws in the sense, like for tiny things, either quantum mechanical or Newtonian equation reports. In this regime, it will show what kind of motion you should expect. And if you go to a higher extent, like the granular system where there is no temperature. Granular systems are essentially governed by the time. And then, as I said, Brownian motion. I'm not going to fix it here because I'm sure that all of you know about the Brownian motion. Like Robert Brown, first time, he used Coulomb grain dispersion and found the Coulomb grains are moving, in a zigzag fashion. And that is what is called Brownian motion. And then, as I said, that because you can see the particles in ordinary lines, you can see their motion in video microscope. And the time scale of such motion is of the order of milliseconds per second. It can be as low as a second. If you compare with the time scale of motion of, let's say, atomic scale, the number of the order of, in fact, of water molecules to move is about 10 femtoseconds. 1 femtosecond is 10 to the minus 15 seconds. Whereas this time scale is 10 to the minus 3 seconds. Okay, so you can see, this simple because of the size, they move slowly. Because they move in a dispersion, the dissipation of dispersion is possible. That also has the motion. Another interesting thing, in fact, this is what In case ABT, we take room temperature. This is common is only 40 millielectron volts. So you see the energy scale is so different. This is what makes the system interesting in one sense. Like it is essentially means that if you put small energy, which is comparable to the room temperature energy, you can part the system heavy, which is not possible for atomic system. But that is what actually makes colloid interesting, let's say, plethora of activities to understand quantum matter systems. They mimic quantum matter systems, but at the next scale, where the system can be easily, let's say, tailored, and one can monitor the motion in real video. Nowadays, it's possible to have video microscope with the shutter speed of milliseconds, and you can actually see where to move, which you cannot do in actual system, quality systems. So in fact, this is something like you can actually see frame by frame how they move, and that happened already 30 years back. People didn't know how to make video microscopic systems. So clearly, any system where the energy scale is so low can be perturbed. Many partitions people use shear flow, chemical gradient, and many other things. I put that in red because this is the kind of system that we should be talking about. And more importantly, apart from its pedagogical influence, as I said, that they mimic systems of quantum systems which can be experimentally probed easily. One can see how the particle moves, which is a remarkable thing, and also important technological properties. Many systems of this kind, in fact, two systems that we discussed, both of them are technologically important. Now, let me come to the particular topic that we would like to discuss today. This is what thermo-responsive. Now, what thermo-responsive? See, it's something that we expect that if you put a system where one part of the system is hot, other part of the system is cold, then particle will move from hot to cold region. That's a normal tendency. Now, in this kind of system, something additional happens. In a system like this, the interaction between the particles, so what we're talking about is called interacting particles. Interaction means you can define a potential, derivative of which will give you the force acting on the given particle. Now, the interaction is characterized by different parameters, and the interaction of this kind of these systems actually changes as it changes temperature. Say, normal what happens. If you take, for example, real gas, the interaction between the particles is given by the Reynolds interaction with epsilon times, let's say, sigma by r is equal to 12 minus sigma by r is equal to 6. Now, this epsilon sigma does not depend on temperature. If you change the temperature, then epsilon is scaled down by kV. And that's a trivial scaling that happens because of temperature. But what we are talking about here is something much more. What happens in this kind of system, talk about concrete system of this kind. In this kind of system, even those parameters that define the interaction will also depend on temperature. Now, if I think about Hamiltonian, the Hamiltonian consists of the temperature, kinetic energy, and potential energy. Kinetic energy of the potential temperature that our kinetic energy is the temperature. But that is what defines the energy scale of interaction, which is the scale epsilon by kT. But in this kind of system, epsilon, sigma, they themselves become temperature. Okay? And that's the difference. So not only the scaling that comes from the kinetic part, but also scaling that the change that happens in the interest part itself. Hamiltonian itself is something, of course, you can imagine that this system is not only linear, it can be only steady state. So, because of the fact that the perturbation between temperature will change the parameter itself. Okay? So, if you think of a system where a part is in cold region and a part is in hot region, then of course the parameters will be different temperatures, the system will be in some kind of motion all the time. And a situation, if it comes, that the flow from one end to the other is counterbalanced exactly by the flow, the system comes to steady state. So the question is asking, what happens to a system like this? Okay, a couple of examples that I should use today. One is linear metal nanoparticles. Though are nanoparticles, but they really belong to the colloidal chain. So something of the 50 nanometer, the critical size of those nanoparticles. And thermo-responsive hydrogels. These are the two systems in which this current thermo-responsive behavior will be shown. What we are interested in is the steady state as a practice state, how the structure forms. And this is not trivial, right? Because we know that if you cool a system, then the system goes from, let's say, gas, then condenses into liquid. Further cooling will take in a particular pressure force, will take you to the crystal phase. Now, this is very important because the changing temperature and the system will come to equilibrium, will show different kind of structures. This system, as I said, inherently in steady state. As a result, it is not solved. Whatever that will go in equilibrium will also follow here. For example, the system will form a long-range pattern. Now, say, imagine that the system is already having flow, right? And the long-range pattern that we are talking about will survive even if it is a closed system. And this is not important. We're trying to see if that is possible or not. Then, if possible, then what is the next? And what if I give you the parameters of the steady state, how the structure evolves? Like imagine how the steady state structure changes from one kind of pattern to another kind of pattern. I'm using the word pattern because in steady state situation, polymer phase is getting this form. There is no real phase in the steady state situation. You can have structural pattern. Now let me see. I mean, if I cannot tell you everything is fine. I mean, asking questions and have one clarification. I'm trying to go slowly and try to explain the basic ideas. So, kind of system where the ligand, so let us come to ligand and metal nanoparticle system, which is thermo-responsive. Now, in experiment, what will happen? An experiment was done in IIM in our. So, they have taken metal nanoparticles, typically gold or silver. Now, the nanoparticles by themselves are not stable. Typically, put coating over the nanoparticles to stabilize. And coatings are done by the so-called ligand, small molecules. They are all typical organic molecules, which are sort of, put a carbon within the nanoparticle. And this kind of carbon actually tries to stabilize the system. Now, just imagine that we are taking, let's say, a volume of such nanoparticle with water, and then you sort of prepare it, start it time, and then you put a part of the pipe into it. So it's something like this. You have this pipe. Upper part is, let's say, initially before the second room temperature, and there was dispersion, this kind of nanoparticle with water, and then this lower part you put in fridge, and the upper part is still in the room temperature. So what they find that in the lower part you find to form stable aggregates, and these aggregates are really, really large, and these aggregates can be used for something called surface enhanced Raman spectroscopy, which is capable of finding, let's say, some trace element apart from building. Just because surface area has increased, enhanced surface area can be used for a better Raman probe. And so that is one of the things which people think that can be used for sensing bombs and explosive chemicals. Okay, that's why we do it. Now, for their system, of course, we are not interested in the bombs though. We are interested in what the physics of this kind of aggregate formation. So it's like aggregate of the experimental system. We have put, so this portion is cold. We have put cold in both regions just to make sure of certain boundary relations. So measures in the zeta potential. What is zeta potential? See, metal nanoparticles, they have the charges on the upper. You know that a metal can have charge on the surface, right? Gauss's metal response. So, and these electrons which are on the metal surface forms what is called plasma nodes. Plasma nodes essentially because of the electron difference surface. Now, if you take two such metal particles, because of the charge density which is collected to the surface, they tend to repel because of the same charge on the both surfaces, and that is purely electrostatic. Okay. Now, as I pointed out, that typically such particles are, in fact, that's the reason that the particles are not stable, because they repel and then in fact it is very difficult to stabilize the solution like that. Huge energy to stay, because as I imagine, they will try to take away from each other. So as a result, putting some container which is required for different technological use, for example, is very difficult. That's why we try to coat it, ligand coating, so that it can stabilize. Now, the kind of ligand they have used for this is citrate ligand. And what we find for these systems of this kind, as the temperature changes, the zeta potential falls off. Now, falling zeta potential means the system actually takes a small amount of charge as you go to lower temperature. So essentially what happens, the effective charge of the system is increasing. Here you can imagine the electrostatic potential is increasing as you go to lower temperature. So essentially this kind of system shows sensitive interaction, because as you can imagine, the electrostatic governs the interaction between the particles. Okay. Now, this is the kind of system we are trying to understand from bottom calculation. The model is proposed as follows. First of all, so it's a calculation of the system that we are trying to study. Initially, it was a top temperature, then we put the two sides between hot temperature between. Now, we put the interaction of the particles. So this kind of cartoon of the particles. So they are like the ball and the hairs all around, and these are like short layers. Now, the interaction between a ball without the ligand is simply given by this kind of potential, which is known as strain Coulomb interaction. What does strain comes in here? See, because you have net surface charge, so any kind of impact, most of the solutions have got solved. Now, these salts, that's not opposite ions which collect near the surface, and that typically screens the electrostatic interaction called singular interaction. And then on top of that, there's another interaction which comes in because of the fact that these are not, these ligands are, they are electrically neutral. Now, since they're electrically neutral, you can think of these, pairs as some kind of hydrophobic entity. Hydrophobic is what? They don't like water. Okay? Now, why is it like this? See, typically those ligands are formed by means of alkane, methyl CH3 group. CH3 group does not have any charge. As a result, remember what is polar molecule? So polar molecule will find interaction favorable only if the other outer part is polar or charged. If there is no charge, then water does not interact with those entities. Right? Those entities actually are not liked by water. They will try to repel water as much as possible. That is the main mechanism of stability of the surface system. Okay. Now, how the temperature sensitivity comes about? I'm not going to details of mathematical details of this equation. Let me try to understand, by simple physical understanding. So, you see that as you coat the surface with ligands, see the ligand has got, sulfur group, which is like sulfur with a positive charge, and they actually bind to the surface. As a result of this binding, the next surface charge goes down, right? Because a lot of charge is given up through the binding of the is also called anchoring in the language of chemistry. So in fact, this is a subject where physics can go hand in hand. So you cannot understand such atoms in chemistry. So they actually tend to neutralize a lot of surface. So you can imagine, this is a potential will decrease. Now, if you go to a lower temperature, then clearly the number of such ligand bound clusters will increase, right? Because if you go to the temperature, body temperature helps the system to be stabilized. So the part of the ligands which collect to the surface will remain, and then the binding will be stronger at a lower temperature. So as a result, you can imagine that the zeta potential will decrease. And that is what Dr. Ashton mathematically showed that these are not compound. They can couples of this inversely. They are dependent on zeta potential on calculate the A and Z0 for zeta potential. And zeta potential, we know in experiment that they depend on vector constant temperature. So for the experimental data, you can actually calculate those quantities which is consistent and how this is also. Now comes this. See, this one is a very strange one. See, if you have two particles which become water, mix them in water, then what will happen? They try to water out as much as possible. And what the best situation, the two particles are so close that water becomes difficult to replace. And this is what is known in chemistry called hydrophobic collapse. The particles actually can't zoom. They actually touch each other. And this is one of the major forces by the high volume proteins stabilize the suspension. I'm sure that all guys know the protein actually has got tertiary structure, the functional unique in 3D structure properties. There's one more force, which is the hydrophobic. But the major force why the protein goes is that the hydrophobic part, protein is a molecule that is both hydrophobic and polar. Polar part is exposed and hydrophobic part should be very precise for contaminating the and that is what it drives. Now we have similar idea here. Now imagine that if you have two particles in a with a separate, what will happen when the water will cool inside, get inside. So that's not ever, right? They will try to come back and water will stop. Effectively, it's like spinning. And this kind of precisely is that effect is taken up by this method. And spin constant is a tendency to move water out. And this spin constant, you can imagine, is proportional to how many ligands. You see, ligand binding is controlling the hydrophobic tendency, more ligand is more hydrophobic. And at the same time, ligand binding actually sort of activate the surface charge more. That means the intercrystalline interest will increase. So it's an opposite tendency. And clearly this tendency becomes different and controls the binding potential. So this is what we have taken up in our calculation. And then this is a pure simple simulation. Okay, what is done? Like you can think of the Hamiltonian, then you can write an equation of motion which is essentially called the Lagrange equation. And from that equation we can derive a simple manner an equation like this. We don't know about too much about this. All it tells that a particle position at time delta t per delta t is given by the particle at time t, and then there is a force acting from the system, and this force consists of all possible forces in the system coming from other particles, could be from external source as well, and then this damping. What damping comes from? Again, don't forget that the system is a dispersion. So as the particles are trying to move, the particles get the cap nanoparticle, the ligand cap nanoparticle, as they move. They experience viscosity of viscous drag of water. Just think of just simple damp oscillation. So that's a typical model. This is the first model that concerns the effect of damping on motion. So it's something very, very simple. And then you have a noise term. Why the noise comes about? See, this is something as follows. As the nanoparticle trying to move, they calculate the solvent particles at the dispersion medium. The medium particles are so numerous that the force acting by them cannot be given so easily in terms of simple numerals. Instead of that, Jaydeb proposed that because the force is numerous, we can simple in terms of statistics. And what kind of statistics? So the force is a statistical object whose variance is given by actually it's not written. It is given proportional to d into delta. And this is the force that is acting because of the fact that it is medium. So medium is not explicitly taken into account. But medium effect is taken into account by using the viscous acting and the price. Why do you like this? You know, the reason is simple. I'm just one word like to say about it. That medium particles are much faster. As I told you, this kind of system should have huge difference in time lengths. Medium are much tinier and much faster. So if you want to do a computer simulation where you take that medium part explicitly, then most of the time you go to understand what the medium part is. We are interested in the medium part. Big particles. Then this thing comes. And that is what this thing is, in fact, I tell you one thing. Even today, we don't have any better scheme than this. So this is the scheme used to understand molecular mechanics. So it's a paradigm of molecular mechanics.
The force actually, the random force.
Yes.
If you calculate the correlation,
Ah.
so that will be derived from
Yes.
multiplied by.
So therefore we get this.
So that should be multiplied by derived.
No, this one already, so basically if you assume that the force is like this, so then the variance is the one that you need to modify. Variance was like b delta t, and the square of variance is this. So this is actually it's a very bad way of telling the things. But this is a simple way to understand. Square of variance will be this stuff.
Actually, the different time correlation should be derived by.
But it's in fact it is yes, but this is a different time. The time delta t minus yes. Yeah. Okay, now in this case we make one convention though, because the system has got two different temperatures, the diffusion okay, so this is a diffusion coefficient. Okay, that's something diffusion coefficient is what? Like say if a particle is normal Newtonian particle, then you know the velocity so displacement is proportional to that. And the question of velocity. In a system like this, however, linear distance doesn't make sense because the particle can obviously affect. So if you think of long time average, it will be zero. Nevertheless, there has been some displacement because of the random displacement. Hence, the meaningful quantity will be square of displacement. So it's called mean square displacement. And mean square displacement is again linear in time. And there's a huge theory of that. This is one person who knows the theory much better than me. And this proportionally constant is the diffusion coefficient. Okay. And then, okay. So this diffusion coefficient depends on temperature and is proportional to that. So larger temperature, in fact, for larger temperature it will be more. For larger particle it is less. Now this is how the balance goes in. Perfect balance nature. And then, okay, so obviously we consider that this diffusion in hot and cold is different. And in fact, okay, gamma is also, or maybe for the time for simplicity, we take gamma to be constant. Gamma is not really constant, also doesn't temperature gamma is also taken into account in our calculation. Now let's have to step to the results. So for what we start with a liquid. Now liquid system in Kolkata is a system with short range water. So this is what is meant for what it means. So this tells you, see this is a quantity that tells you if you know a particle at some point, what is the probability that you find another particle at a distant path? Actually R2 particle. Okay? And this probability looks like this. So you see there's a maximum probability at an particle one that corresponds to, so our first word is shell. Then catfish falls up, to almost to 1. 1 is the not, the limit by the system is the non-practical. It's not 0 for reasons which I don't understand here. But this is not. So you see the density So the density correlation is percentage after few layers, and these are called the gold distinctions. Most prominent being first and second strands. So that is called short in order. Gas and then no order. This is not short in order. And a crystal is a long in order. It is not infinite because it is a periodic implication of the space time. So no matter what is in the book, you still see something, right? And hence is so obviously liquid is something liquid. Now, what we do after you get a system like this, we take the two parts. So initially it was this, it was a liquid. Then you pull two portions. And the reason we are taking two portions to the full temperature is because what we want to make sure that if a particle comes from this side, it should again be cold. So that's just because of the artifact of the simulation cost, the finite cost. So in reality, the particle can go as much as they want. But in this case, that's not possible to do that. Hence, we are using the thermo-responsive. And then, what we calculate is the density of, say, now what we have are the two regions. This one region and the other. I mean, this was essentially square. They are the region. And if what the density of particles that we just clearly they go to equilibrium at a steady state. And we analyze the system after the steady state is reached. In the steady state, if you look at the density of particles, you see in the cold region density is higher than the hot region. There is a lot of oscillation which is not interface because the cold region and hot region they do not directly go from one to another. It goes to substantial amount of space which is called interface. And then if you go to the cold region and if you start at the same point, you see that there are lots of particles and the thing actually go on to increase the substance. This is the signature of the non-linear. The sharp peaks and no matter how many coefficients that will go. Now once we know that in the steady state the Rockman order is formed, we try to analyze what is the structure. Now how do we do it? So the way that we do, now what is the ordering things that just think in terms of simple hexagon. There are some examples to understand. Suppose we have hexagon, then the Venn diagram is already up there. No, I started late. 4:15. Yes. So it's not happening. Right, and I started about 4:15. Okay. So now forget about those mathematics. Simple thing in the book. Suppose we take a hexagon. Now in hexagon, if you think of particles, they are at the vertices. Take a regular hexagon because that's very resistant. Now you see you can actually think of bonds between the particles at the corners. They are very specific angle, right? The angle can be valued. And the angle information comes through so-called spherical components, right? Because that tells you the angle information. That's precisely what we do. We take a bond, we decompose the spherical components. Now, what I say in example in theory, in theory, of course, you can think of another thing in terms of the polarized as a movement. So this is a decomposition that we do. And then from the coordinates, if you know coordinates, you can decompose, right? So from let's say if you know what I am J particle, the reverse separation vector, you know corresponding Cartesian components, right? Sorry, polar components, spherical components. It's not unique, so it's a little recursion, different mechanism. Never think it's possible. And once you do that, you can construct quantity which is called A. So you see that this is summation of n to this dimension of L. N is the azimuthal component. And basically, this tells you the order of the system. Roughly. Now, we do suppose now what we have the entire system. The particles are in different places. At a given time, you can compute this properties in all the particle coordinates that you get from solving equations of motion of this kind. So if you know the equation of motion, then you know the separation between all those pairs, and you compute this quantity by knowing the corresponding spherical coordinates. And then, so this is an observation. People have characterized this kind of diagrams many years already. So for each particle pair, you must assign what is the L equal to 6 value and one L equal to 4 value. See, L equal to 6 corresponds to hexagon, L equal to 4 corresponds to the squares. This is the predominant order. One can even for 3D. The axis lines, for example, can be called layers of hexagons. And this is lines can be called in terms of layers of squares. So that is why these that Q4 are the predominant quantity that we use to have the structure. Now remember, for each pair you can do that. So if you find a hexagon, then put a point. Then if you find a square, Q4. So basically you put the point. So for each particle, you put the value U6 plus Q4. It's like a correlation diagram. So you're in a correlation diagram, right? Suppose you have range X and 1, you can plot X and Y and find the so-called correlation diagram. It makes sense. For each particle pair, you can give U6 and Q4 and just look at the correlation diagram. Now this region is known to be this is a node. We are not doing this for ourselves. In fact, it is now known what parts of the XCT, what parts of the XCC, what parts of the PCC, so pretty well, characterized. And of course, what we find is liquid. Of course, we get liquid because we remember that we had a system where, so this is a kind of system where the density is low and that liquid, of course, it has to be in the hot region, and a cold region high density, and that should be solid. Now, this horizontal diagram really supports that, but it tells in addition. So, when I say solid liquid, I said the solid liquid which says is more than that. Now, what kind of solid is that? This is what we're trying to figure out from this kind of diagram. So, we find that the region which is solid is more than PCC, and the region which is liquid, the part is liquid. In between, of course, there is an overlap. That's the integration. Okay. Next, what we do, the question that we ask. So we know the system is, say, something like this. Initially, we have at hot. Then we do the two sides, taking the medium, the middle is hot. Now, as the particle flux is taking place from hot to cold, then clearly, see, physical is an extreme simple. There is nothing so great about it. What is happening? That the particles are moving from hot region to cold region, and as they move, and that's a typical, common diffusion. A particle will go from hot to cold. That's what you know, right? And as it goes to cold region, they slow down, and they have enhanced interaction of the hydrophobic region. And you see hydrophobic interaction tend to collapse the particles, and that's the simple thing. Okay. So now the question that we ask, that we start from time, the moment you create the interface, this is time 0, and then you progress in time. How much of the let's say particles in the hot region, the cold region, is converted to PCC? So that's a simple counting. If you have say total number of particles you want to do, you count how many particles of that region is. Why? How many? Because not that all particles are PCC at the same time. The interface. It's impossible to look at the interface. So we just make a simple count to the cold region and find how many particles are converted to PCC. And this is how it works. It shows 3 steps. First, it is slow growth. The particles going to the cold region, they slowly try to get together. So that's the first slow growth. Then once sufficient amount of particles has gone there, which we call integration, then it rapidly changes. But in the end, there is not too much particles available for conversion to BCC, then it happens. So this is how the creating goes. It has got 3 stages, and this is also, it's also known as Abnani model. Because Abnani model describes this kind of kinetics, how the phase will, let's say, the ordered phase will grow from disordered phase as you tune some parameter of the system and you just start the system at the time. So this is, in fact, okay. See, I mean, for this system, the phase diagram is not, steady state diagram is not. But you can take your simple system where we can actually try to study the steady state diagram. So the system is Lennard-Jones. Previous system was of Lennard-Jones. It was actually, combination of so-called spin Coulomb interaction and hydrophobic collapse interaction. Here we take what's in the interaction, which are sort of familiar with, all these are familiar. But as I said, the only difference is that we take external dependent on temperature. Here also you find something similar. The crystal, the core region we find the rounded number. And this is a kind of diagram, I'm not going to explain that too much. It's already here. The only difference we come here that the structure of the crystal is FC is 26. Okay, in fact that is sort of more to do with the how strong the individual attraction is. So that is the side for kind of taking it. Next thing that I have the derivation is another system, the hydrogens. What hydrogens? Interesting system. These are the systems that we get normal, like particles. Examples are silica hydrogens, which are used to, for example, when you protect your clothes from moisture, then you put small, spherical balls. I'm sure you are listening. In the supermarket, if you go to a good shop, they put something in the pack that's small scales. And these hydrogens, they are absorbed. And those hydrogens have not at all chemical like this. A class of hydrogen has got a polymer. So if you change the temperature, then at high temperature the hydrogens form. It takes a lot of water. And that is why it is so important in our country. You need hydrogens to protect water from moisture. As the lower temperature, they release water and they become smaller. Okay, and there is an equilibrium between these two cases. Now, if you take a system like this, there are almost again this is a system where interaction is sensitive to temperature. So we try to model the same system, but it's only the difference that we do here. Unlike previous system, so okay, I should point out why we are taking external temperature here. Just because in the end, as I said, the interaction, the total sum of interaction between the two particles, the combination of microscopic collapse and the spin collapse, how the depth of the interaction is changing, the vector of this difference. Apart from that, the interaction still has to go. It is sufficiently, let's say, interacting. The interaction is sufficiently strong to make sure that it crystallizes into a certain form. Now, so that's the reason we have taken external dependent on temperature. In this system, of course, what we do, we take external samples, but we take sigma variable. The reason is simple, as I said, the size of the particle actually changes as it goes from one temperature. So this is what they always take, and always the dependent on, as I said, is also this experiment was done sometime back, not in our country. The dependent was done now. And nevertheless, now something very strange happens. What happened now? Okay, I'm not going to tell you a lot of details of mathematics and results. I try to explain in words what is that you get, you expect and what you get. See, as the temperature can imagine, the particles will tend to go from the order. That's something Yeah, cold temperature, this is bigger. This one and this one are not numbers. Is it? So this is diameter as a function of temperature. Yeah, hot temperature is smaller and cold temperature is bigger. Yeah, so I'm sorry, it's not cold. So it loses water and that's something wrong with it. I mean, if you have water and then you heat it, they lose water and it becomes some smaller particles. So if you go to hot temperature, the particles, the water will come out and particles shrink. So now, as the particles go to the cold temperature, from hot to cold region, they swell. They not only slows down, they also swell. Now, as they swell, no particle can go because particle is limited by the space that is given to the other particles when they try to get inside the cold fluid. As soon as that happens, the particles are sufficiently big and number of particles in the cold is sufficiently large. The hot particles, even though they try to get inside the cold region, they repel back. Now what happens effectively? The hot region, the cold region is already large and let's say, the packing in the hot region already is high because of the higher size, they can form crystal. Because whether the system forms a crystal or not, that will be decided by the packing. If the packing is high, then this crystal, the packing is low, then it can be that. So there is this simple that if the packing is low, that means there is enough freedom, there is enough room for the particles to go about, and as a result, this is not possible to crystallize. Now let's think of what will happen to the hot region. In the hot region, the particle numbers are now higher. These are increases. That's because the cold region cannot hold those particles. So normal tendency, again I repeat, the normal tendency will be the particles will go to the cold region and will try to stay there if it is less. But as this happens, then the particle number in the hot region, in the cold region will increase because the diameter is increasing. It cannot increase forever. At some point, the particles which tend to go from hot to cold region also revert back because they don't have sufficient space to leave the cold region. As a result of that, the population in the cold region, in the hot region will increase. So even though they have smaller diameter, the population is higher. As it is in packing patterns, it can be in comparable packing. As a result, particles in the hot region increase. And very, very strange. We normally know that the hot, in hot atmosphere, the particles tend to be liquid phase and of course can as well be gas phase. In this case, because of this space, pure non-equilibrium, because it's happening because the particles are dragged from hot region to cold region. Cold region, the particles will grow bigger, so they cannot hold in too many particles. The particles will now revert back, and in the cold, as a result of that, the hot region, the particle will increase, and they may get, of course, as it may, it will depend on the details. What is the packing gets hot and etc. So if so, that will mean that the effective pressure in this increase is enormous. The reason is, the hot region is having, cold is having a lot of big particles, they will put pressure. And as a result, the cold region, the number will increase. So there also the pressure will increase. So the equilibrium pressure and the steady state pressure will be enormous, maybe enormous. That's what is happening. So this is kind of how the flux analysis. Clearly, if the flux from hot to cold and cold to hot, if the net thing is negative and this is slightly negative, and given that goes to okay, this settles to something like minus 1 so it's a negative. So that essentially means the cold region, hot region flux is also larger than the reverse flux. I just decided the size of it. But this happens after long, it does happen instantaneously. And if you now after steady state you can complete the pressure, of course you have to be careful, the pressure carries anisotropic pressure tensor, and the trace of pressure tensor actually is much higher than human pressure. And that's something as I tried to explain to you is something that you would expect. And that's the kind of steady state structure of diagram which shows that the eventually, first of course one expect that the hot region, liquid, cold region is a crystal. Then the cold region remains in crystal, but the hot region also crystallizes. Okay, this is something very, very strange. This is not possible because it's simply purely equal. Is an example of how non-trivial effects of the steady state behavior may be different from trivial behavior. Okay? And again, in this case, the hot region, like I said, I showed earlier, appears to be in both the regions actually asymmetric rather than exoteric. And it also something that we find recently. The kinetics of those regions are not the same. Like the kinetics of crystal growth in the hot region and that in the cold region are different, which of course things are yet in progress. So take home message is simple, that it is possible to use microscopic particles to generate long range order in the crystal temperature gradient or temperature difference. And more interestingly, it's possible to have hot crystallization long range order in a material, even the hot region, with particularly talking hydrogen systems. Let us this here some of the current. So this is the work. One kind of activity that we have done over the last few years. There are other activities that is going on in this group. Like for example, we study the most of colloidal particles for polymer effect, and this is useful in designing mass and reverse process. Then we also study the viscosity property of confined systems. We also currently look at the of confined polymeric materials. We also look at the liquid cell assembly of near chemical particles, very similar system as this, right? We also look at the molecular colloids, the dynamics of this behavior, and not to mention this, a lot of things that we are trying to do biomolecules. Biomolecules are very strange software systems. It's a system where even quantum mechanics goes on. Why? There is a hydrogen bond that requires quantum mechanics. So this is a unique system, but it combines the classical ideas, the classical simulation that I described. So it's a system classical one, a big part, right? In protein, for example, it's a large thing called niche, but the interaction at the final level, the microscopic level, may be a product of nature of this thing. So, and of course, my acknowledgement will be to all the students who are sitting behind, but there are a few more who want the biomolecular done because they said this is not their top team. So they did. Mostly who are working on the those things are here, except Kolkata does and the one that I covered here is Rahul's work, and he will submit this very soon. And right now we are in the process to write the papers, particularly the paper of the population which I think is quite exciting, and he is trying to look at the aspects of it. So with that I will have to thank you.
Okay, that was the end of a very interesting talk, and if anybody has any questions, queries, comments, I think Professor Chakraborty will be happy to respond. Yes.
Could you please show the phase diagram? Actually, two values. No, epsilon star. this one. So I think the bound it segregates the solid liquid, liquid, liquid. So is it linear in this term?
See, that I cannot comment because the phase boundary is very schematic. It has not been looked into so much. Just look at this way. So I don't know. If you can numbers back from here, I will do this.
Cannot try to get it as a linear function of this term.
I am not. So I don't really know. See, I think the main problem is in a system like this, where you travel, how to describe the transition. First of all, we will not know the clear transition. We have to factor in, for example, the specific. Okay, so I cannot really assert that there is a phase transition. So that's the reason I'm using structural diagram to be on the safe side. I'm not using the word steady state phase transition. So unless in the phase transition, I don't know what the good way of describing a system like this. So one might try, for example, some kind of where again I make sure that one of the physical variables should be the order factor of the solid. So that I know that one again I don't know how is it.
Because that is kind of model with cellular autonomy.
Yeah, but for sure.
Okay, thank you.
Okay, so other questions students? What's the understanding of orders too difficult or too lengthy to understand this?
Okay, maybe they will find some questions later.
So if you have questions in future,
Yeah.
because I thought that you have taken video of the thing, right? So if any question or if your friends listen to the video, if they have questions in mind, they can always write back to me. You can get the email address through the website in our homepage. All the email address is there.
So any queries, you may please ask through email to Professor Chakraborty. So in that case, I think we can conclude this session. Thank you very much for a very nice talk.
Okay, thank you.